Hello, everybody. My name is Andrea Malchiodi, and I'm current director of the Georgi Research Mathematical Center. So welcome to Pisa. I'll just say a few words about the center. I promise I won't take much of your time. The center was founded about 25 years ago, formally as a research laboratory of Scuola Normale, but with the aim of creating opportunities for the mathematical community in Pisa and visiting Pisa to gather. The main activities since the foundation have been workshops, schools, intensive research periods, and we also have a colloquium series. We have visiting positions of two types. So there's opportunity to run research in pairs or groups. And also we have postdoctoral positions of 2 years. Usually the opening is in November, December. Basically, that's all I wanted to say. I would like to thank the organizers for bringing up this interesting event and also the staff of the center for the constant and valuable support. Thank you.
Oh, thank you very much. Thank you for this introduction. Thank you for having me here. I'm really pleased and honored to be in this wonderful place for what I'm sure will be a wonderful conference, a wonderful workshop, perhaps once the first talk has passed. But so the title mentioned gamma convergence. I'm not so actually sure I will get to the gamma convergence part. I want to keep my talk very elementary, very introductory, and mostly self-contained as much as possible. That also means that necessarily it will be boring to someone. And if so, I apologize. I'm sorry. But most importantly, this is joint work with Ramon Oliver Bonafù from the University of Verona, Gian Domenico Orlandi, also from Verona, and with Van Phu, which formerly was at the University of Verona and now is in Heidelberg. And the topic is a convergence result, nonetheless, for manifold-valued maps. So let me set up the problem I'm interested in. I have a domain. Omega is a bounded and smooth domain in Rn. This is the domain where my maps are defined, and the target is a manifold. Precisely, it's going to be a submanifold. I call it curly n. It's a submanifold of sub-Euclidean space, Rm. It's a smooth, compact submanifold with no boundary. It's connected. I'm not writing it down, but it's connected. And then we have an exponent p. P is finite and strictly greater than 1. And we have a boundary datum. The boundary datum, I call it G. It's in the appropriate trace space. So W1 minus 1 over P, comma P. The domain, well, it's defined on the boundary of the domain, and it takes values in the manifold. And by this notation, I mean that G is a W1 minus 1 over P map from the domain, the boundary of the domain with values in the ambient target, in the ambient space, Rm. And moreover, G of x belongs to the set n, which is a subset of Rm, for almost every point in the boundary, almost every with respect to the surface measure, of course. And I'm interested in minimizing the Dirichlet, the p-Dirichlet integral. So I call it dp. It's the integral of grad u to the power of p with respect to the Lebesgue measure over the domain omega, and a minimized subject to given Dirichlet boundary conditions. So I minimize in the class W1P. G, here G denotes the boundary values. And again, I'm interested in maps with values in the manifold n only. So once again, this space is nothing but the classical Sobolev space W1P with trace equal to G on the boundary. It's a subset of W1P omega with values in Rm, but I impose additionally that the elements here take values in the manifold n for almost every omega, almost every point in omega, sorry. So now, so what I'm going to do, there's plenty, minimizers of this problem are called minimizing p-harmonic maps. There's plenty of literature on these objects. They're very, very studied. For instance, there are many regularity results. There's not necessarily a full regularity theory in that sometimes minimizers are discontinuous even, but there is a partial regularity theory going back to the late 80s with works by Hart and Lin, and then more recently there's quantitative partial regularity theory, so there might be a singular set, but you have estimates on the size of the singular set, for instance, estimates on the Minkowski content and so on with Naber, Valtorta, and Veronelli. But today I'm not so much interested in regularity. I'm interested in existence of such objects because, well, it's very easy to prove existence for this problem. So existence of p-harmonic maps, minimizing p-harmonic maps, so long as the set here is non-empty. But sometimes the set is empty. For instance, suppose your target manifold is the unit circle. This is an example I will come back many, many times over my talk. And suppose your domain is nothing but the unit disk in 2D, and your boundary datum G is just the identity on the boundary of the disk. Well then, what are you doing? You have a boundary datum such as this one, and you're trying to minimize a certain integral among unit vector fields on the disk. But you have a boundary condition, and the boundary condition carries a non-zero topological degree. So it's impossible to extend continuously the boundary condition inside the disk. If you try and find such a continuous extension, you'll fail to do that. At some point, perhaps somewhere here or somewhere else, you are forced to introduce some sort of discontinuity because the boundary datum has non-zero degree. And as a consequence, my Sobolev set W1P with boundary value G from the disk with values in S1 sometimes is empty. This happens, for instance, if P is strictly greater than 2, because in this case, you have Sobolev embedding of this into continuous map, but there is no continuous extension of my boundary datum, therefore there can be no extension in W1P of my boundary datum for P greater than 2. Actually, it turns out that for P equal to 2, you don't have the Sobolev embedding into continuous functions, but still, it's true for topological reasons that this set is empty. So heuristically, if you will, W12 maps in 2D, they're not quite continuous necessarily, but they're very close to be continuous, and therefore the same sort of topological obstructions that apply here in the continuous case apply in the W12 case as well. And this can be all proved rigorously. I won't bother you with the detail, but there's references for that if you're interested in. So in order for me to proceed further, I need to introduce some notation, because you see the possibility of minimizing this functional seems to be related to some sort of extension problems. I think we might have a little bit more on that respect in the next talk, but I'm not sure. We'll see. But anyway, let me set some notation. Let me define some k depending on the manifold n. This is going to be the smallest integer, positive integer, such that there is a continuous map from the boundary of the k-dimensional ball with values in the manifold with no continuous extension inside the ball with values in the manifold. So k is the smallest integer for which my extension problem, so to speak, fails if we are considering a boundary datum defined on the boundary of the k-dimensional ball. My manifold is supposed to be connected, which means whenever I take the interval, the one-dimensional ball, and I take a boundary datum defined on the boundary of the interval, this is just 2 points in the manifold, and I can always connect them by a continuous path because my manifold is supposed to be connected, which means k is always going to be strictly greater than 1. At the minimum, it's equal to 2. Or it might be larger, but it turns out that whenever you have a closed manifold, so whenever you have a manifold that's compact and has no boundary, this k is always finite. Sooner or later, you will find a continuous map defined on a sphere which has no continuous extension inside the ball. And for instance, in case your manifold is the unit circle, the corresponding k would be equal to 2. This is one example showing you that already for the boundary of a two-dimensional disk, sometimes you cannot extend continuously. And so on and so forth. For higher dimensional spheres, if n is the sphere of dimension L, then k turns out to be equal to L plus 1. And so on and so forth. It doesn't have to be always related to the dimension, it's related to the topology. And why is this k important in this business? Because it turns out that if your boundary datum G is in the appropriate trace space, 1 minus 1 over pp, and p is strictly less than k, then my space, the one I'm interested in today, GW1P, W1P with boundary value G, this is always going to be non-empty. This is a result that was proved, I believe, by Achtenlin in the late 80s, which means the first value for which you can, you fail to have an answer to the extension problem in the continuous setting is also related to the first integrability exponent for which you fail sometimes to have extension in the Sobolev business, in the Sobolev world. So there's a relationship between the two. So what is my goal today? Well, now I take the first possible trace space in which the extension properties sometimes fail. So I take G to be in W1 minus 1 over KK. I take UP in W1P with trace value G, minimizing the Dirichlet integral with P strictly less than K, and I'm interested in what happens in the limit as P tends to K. So this is what I want to understand. I want to understand the behavior of minimizers for this problem as P approaches the critical exponent, which is defined by the topology. And of course, people have done that before. I'm not going to write down references, but I can provide you with them if you're interested. The first results go back to the second half of the 90s by Achtenlin, and then Achtenlin and Wang. They considered problems in dimension equal to 2 or to k sometimes for sphere valued maps. And then more recently, we have a preprint by Jean van Schaftingen and Benoit van Berenberg. This is 2023. They have some sort of a gamma convergence in a way result, I believe. This is in two-dimensional domains, but it approaches this particular question for any possible target manifold. So it's limited to two-dimensional domains, but it carries over to any possible target manifold. It's quite general with respect to the target manifold. And even more recently, this year, 2025, we have a preprint by our brave organizer, or a subset of our brave organizers, Michele Caselli, Mattia Freguglia, Nicola Picenni. They have a gamma convergence result for this very problem in arbitrary dimension. Correct me if I'm wrong, but the target manifold is a sphere. And having spheres as a target manifold is a very interesting case because it turns out to be related to the possibility of approximating the area functional. I will go back later on at the very end of the talk to this particular point. So I suppose they were motivated by the possibility of approximating the area functional for some reasons that will be apparent later. And they were looking at the target value, target manifold, which is a sphere. For us, it's arbitrary dimension in the domain. The target manifold is not quite a sphere, but it's a bit more general than just spheres. But still, we are not able to do any sort of compact manifolds. We have some technical restrictions, which will be apparent later on. And then, of course, this sort of problem has connections with the Ginzburg-Landau literature, with some other sort of discrete problems or non-local problems, if that rings a bell. I'm happy, but otherwise I'm not going to go into details of that because that would take us very, very far. Please do feel free to ask questions at any point, by the way, and I'm sorry, I might run a bit, I hope I won't run over time, so just be very harsh with me, okay? If I am late, just tell me to speed up or something. Now, I'd like to, my goal today is really just to state a convergence result, not quite a gamma convergence as I originally advertised, but just a convergence result for minimizers of the functional. But in order to do that properly for once, I need to introduce some terminology. And I want to be very self-contained, even if I'm going to be boring. And therefore, I'm going to start with some very, very basic definition, which I'm sure basically all of you, or maybe most of you, I don't know already. I am still going to give it. So this is the definition of free homotopy class, of free homotopy, let's say. Free homotopy is an equivalence relation on the set of continuous maps from the sphere. In our case, we are interested in sphere of dimension k-1, because it's all related to this particular exponent here, with values in my manifold. So given G0 and G1, they are continuous map from the sphere in dimension k-1 with values in the manifold n. And I'll say that these are freely homotopic if and only if there exists a continuous map G, capital G, from the sphere times the interval 0, 1 with values in the manifold such that G at times 0 is equal to G0 and G at times 1 is equal to G1. So really you have a cylinder. Well, I assume K is equal to 2 in order to do the picture, otherwise it gets a bit complicated. And you really have a cylinder, and you are asking that you can find some sort of extension. You put on the lower basis of your cylinder, you put the boundary datum G0. And on the upper basis of the cylinder, you put the boundary datum G1, and you're asking for a continuous extension of it. And if you can find such a continuous extension, then you say that G0 and G1 are freely homotopic. I really want to stress the adverb freely and free homotopy, because there is no reference whatsoever to any sort of given base point, to any reference point, if you know what I'm talking about. This is really not the same sort of homotopy you use in order to define the fundamental group or other homotopy groups. It's a bit different, because there's no given point whatsoever. There's only maps with values in the manifold n, and they satisfy no additional constraint for the time being. But still, this free homotopy is an equivalence relation. Therefore, I can define a quotient set, which I call gamma of n, a gamma of n is the set of free homotopy classes of continuous map from the sphere in dimension k-1 to n. Now, again, if you know about homotopy groups, this is obviously very much related to homotopy groups, but in general, it's not quite the same thing, not always, at least. And now I want to define an operation on this set. And this is where things get a bit messy, because I insisted on having no base points. So I can and will define an operation, some sort of addition on this set of homotopy classes, except that in general, it's not a single-valued operation. It becomes a multi-valued operation. So it takes values in the power set of gamma n. So you gave me two homotopy classes in here, gamma 1 and gamma 2. Gamma 1 plus gamma 2 is going to be a set of homotopy classes, not necessarily a single one. And by definition, well, I'll give you the definition now. But in order to do that, I need to make a picture, because the definition needs to, well, you can define things in several ways, but I'm going to do it a bit by pictures. So I consider a particular domain, I call it omega star, as a subset of Rk. Omega star is a big disk in dimension k with two holes. So this is omega star. It has three boundary components, all of them being spheres in dimension k-1. There's the big one, the large one, I call it sigma naught. And there's sigma 1, that's the boundary of the first hole. And there's sigma 2, the boundary of the second hole. All of the sigmas, they are spheres in dimension k-1. So just by dilation and translation, I can identify them with the reference unit sphere in some sort of given way or something. I can make a choice and be consistent and identifying all of them with the unit sphere. So how do I define my operation using this particular domain? Well, by definition, gamma naught is going to be an element of the sum gamma 1 plus gamma 2 if and only if there is a continuous map G defined on my particular very, very special domain omega star with values in the manifold n, such that G restricted to the sigma I belongs to the homotopy class sigma I. Sigma j belongs to the homotopy class sigma j for j equal to 0, 1, or 2. So my map capital G here has the following properties. On here, you have a homotopy class given by sigma 1. On here, you have a homotopy class given by sigma 2. And then I consider all the possible ways of extending this continuously on my domain with holes. As it turns out, I cannot achieve any possible homotopy class here on the outer boundary. So when I can achieve some sort of homotopy class in the outer boundary, say gamma naught, I will say that gamma naught is an element of the sum of gamma 1 and gamma 2. For instance, if your domain is, your target manifold is a unit circle, then it turns out that three homotopy classes are just in bijection with the integer numbers. They are characterized by the topological degree. And then things are really much simpler, because when you have a continuous map with values in a circle and it has some degree, say d1 in here, it has some other degree d2 in here, then you can find an extension if and only if you have degree d1 plus d2 on the outer boundary. And this is really just the sum of the degrees in the sense of integer number. In particular, it's a single valued operation. And as a matter of fact, in many other interesting cases, this sort of operation that I have defined right now, it reduces to a single valued. So if you give me, it reduces to a single valued one. So if you give me some homotopy class gamma 1 and some other homotopy class gamma 2, in many cases, there will be a uniquely defined homotopy class that I can put on the boundary, outer boundary gamma naught, sorry, sigma naught, which is given by some sort of algebraic conditions, or topological conditions rather. But sometimes, in general, this operation can be multivalued. There are examples, even interesting examples. In fact, if you look at some sort of materials, biaxial pneumatics, they are believed they have some sort of topological defects which are described, which behave in a way that's really described by a multivalued operation. And because of the multivaluedness, there is some sort of interesting phenomena that happen for this sort of material. Because two given defects with given homotopy class, they can combine in many possible ways, not just one way, but they have several ways of combining. Now, biaxial pneumatics are a bit peculiar in that they are theorized, but they're not experimentally found anywhere, at least so far. But then, you know, whatever is not explicitly allowed, explicitly forbidden is bound to happen sooner or later. So I very much believe that at some point we're going to see really biaxial pneumatics, and we will be amazed by all the sort of multivaluedness of their topological defects that come out of this multivalued operation. For the time being, I am afraid I have to restrict myself to single valuedness. So I assume this operation is single valued in the rest of my talk. In my setup, this assumption is basically the same as asking that the fundamental group is abelian. But it doesn't matter. What I am really doing is that I am assuming that this operation is single valued. And if I do that, at this point, really have a well-defined operation in the standard algebraic sense, and it turns out to have some very nice properties. It's associative, it's commutative, and I suppose it should make sense that it be commutative, because after all, why should it matter whether I put something on the left or on the right? If I exchange left and right, it shouldn't matter too much, right? And indeed, this is going to be always a commutative operation. It has an it has an identity, and it has inverses. So if I assume that this operation is single valued, then at the end of the day, my gamma naught with this operation is an abelian group. And in fact, at that point, I can really identify this abelian group with some standardly defined homotopy group. It will be pi k minus 1 of my manifold, but if you don't know about homotopy groups, it doesn't matter. I've just defined my group. Yes, of course. Look, I don't know about, I'm not so sure this is really, I mean, in this particular setup, this turns out to be equivalent to homology. And at the end of the day, this is why I'm able to write down a result, which really looks like a homology result. And there is a plateau problem in some homological class. And this is all a gift of the fact that I am working with my k, which is the first integer for which something non-trivial happens. So I have Ure, which is isomorphisms between homotopy and homology, and so on and so forth. But otherwise, I really think, if I am correct, if I forget about the fact that I am working with my particular very special value of k, which gives me a lot of information more. I mean, this is not quite based homotopy, but still it's homotopy. And if I were to make this construction for a generic integer, not necessarily the first non-trivial one, blah, 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 what I would get at the end of the day is really something, this is really something that always is in bijection with a set of, not quite the homotopy class, not quite the homotopy group, but it always is related to homotopy groups. Technically, this is always the set of orbits of the homotopy group with respect to the action of the fundamental group. So not homology, not homology. Ah, sorry. Yes. 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 Not commuted, not a billion. Ah, single valued. I don't know. I really don't know. To me, this operation is sort of natural, because when you have, for instance, I'm thinking of material science, and you have some sort of material which is described as a map with values in a manifold, and my manifold parameterizes the sort of internal states of my material. And then sometimes that sort of maps, they really have defects. For instance, even point defects, and then this is a way of saying, okay, I have a defect over there and a defect over there, and then I sort of take an average and look around some sort of bigger contour that encompasses two defects, not just one. And what do I see on the bigger thing? It's described precisely in that way. So in my mind, this is why the operation is natural. In my personal opinion, when you look at this sort of business, especially if you look at it in connection with material science, and really material science, there are all sorts of behaviors that are theorized because of this. And it's related to, I mean, the quick answer is, I'm sorry, I don't know. I really don't know. I don't know. I don't know. But people in homotopy theory, they impose base point, and at that point you get something which is single valued. But at the same time, from my personal perspective, when you have maps, why should I, which sort of base points should I choose? I have no, and so I lose the base point, but then I lose the single valuedness as well. It's complicated. There are things that, well, okay, I'm sorry, I'm opening some sort of, I apologize. We can discuss a bit more about that, but it's really complicated. I don't know. I don't have a clear answer on this. I'm sorry. I'm sorry. I hope that wasn't too confused. I got all inside my sort of tiny O, and then very well. So now I have a group, and then now I can start doing some sort of analysis for real. I can define quantities. I have, for instance, given gamma, small gamma, in capital gamma of n, I can define the energy of gamma, which is exactly what you would expect. This is the K energy. I could replace K with some other exponent P, so long as P is strictly greater than let's go like this. So long as P is strictly greater than the dimension K minus 1. If you want to. I stick with the exponent K because it's the one that's associated with my limit problem, but you could use some other P instead. So the K energy of gamma is the infimum of all the Dirichlet, K-Dirichlet integrals when you let U vary in the homotopy class gamma. And since I have assumed that my exponent, well, in this case it's K, but either way it could be something else so long as it's greater than K minus 1, so greater than the dimension of the sphere here, then you have the compact Sobolev embedding into continuous functions, and then you can apply the direct method of the calculus of variations. It's not very difficult to prove that this infimum really is a minimum. And for instance, I leave a little bit of space here because I want to write down something else later. If my manifold is a unit circle, then we have seen that K is equal to 2, and gamma of n is in bijection with integer numbers, because the free homotopy classes are just homotopy classes really in the usual sense, and they are characterized by the topological degree. So if we are looking at this minimization problem for the circle, what's the way of achieving minimal energy for circle-valued maps of degree d? Well, you just move around the circle d times with constant speed. This is what minimizes the energy. And so it's very easy to compute the infimum of this problem. For degree d, the infimum is nothing but 2 pi times d to the power of 2. There's a power of 2, of course, because this is a quadratic functional when k is equal to 2, as is the case for the unit circle. So this is a very natural and nice quantity, I believe, but it doesn't play along well with the additive structure on my group. For instance, this is not going to be subadditive in general. It doesn't satisfy the triangle inequality. So if I insist on having the triangle inequality, I can define something a bit different. Up. I look at all possible additive decomposition of a given gamma as a sum of gamma i's in my group capital gamma of n. So I look at all possible ways of writing down gamma as a sum of gamma i's, a finite sum, but the length of the sum is arbitrary. And then for each given decomposition, I look at the sum of the energies of the various terms in my decomposition. And then I take the infimum with respect to all of this possible decomposition. It's still possible to prove that the infimum is really achieved. There's going to be, for any gamma, there's going to be a decomposition that attains the minimum in there. And in particular, it's going to be, you might prove, if you want to, that in doing so, you have defined really a norm on your group. So this norm of gamma really is a norm. It's a norm in the sense that it's going to be always non-negative and equal to 0 if and only if gamma is the trivial homotopy class, the homotopy class of constant. It's symmetric in that the norm of gamma and the norm of minus gamma is going to be the same always. And it satisfies the triangle inequality because essentially I've defined it in such a way as to enforce the triangle inequality. So I have something that makes me happy. And if I look again at my circle, I am given an integer, degree d, for instance. I can write down degree d, for instance, say that d is positive. Then I can write down d as a sum of 1 plus 1 plus 1 plus 1, and so on. And it turns out that this decomposition is the way of achieving the infimum of the energy in here, which tells you the norm of d is precisely d times the norm of 1, which is going to be 2 pi. So in general, this norm is going to be a multiple, a constant multiple of the standard norm. Very well. So now I am given a group. I am given an operation. It's an abelian group. And I'm given a norm on the coefficient group. In fact, several norms, but I'm stick to the one that corresponds to the exponent k. So I have a normed abelian group. I can consider flat chains with coefficient in gamma n. I call them bold f of dimension, say, d. There will be flat chains defined in my domain omega with coefficients in this particular group with the addition that I've described before and the norm that is given in here. Of course, if you have a generic group which might have finite order or in any way contain a torsion part, perhaps you cannot define flat chains by testing against the differential forms as you would usually do in terms of currents and so on. But still you can define flat chains. This was done, for instance, by Fleming in a paper in the 60s. It was based on Whitney's book on geometric integration theory and of course the previous paper by Federer and Fleming and so on and so forth. What you do is that you start from polyhedral chains, for instance. This is something that you can define quite easily, especially if you are in a Euclidean setting, as we are. Because polyhedral chains, basically, I mean, you have to define the boundary operator, but that's very algebraic. You have to define the mass, but you can do that thanks to the norm that you have in here. And once you've got the boundary operator and the mass, you can define the flat norm a la Whitney, so in the geometric way. So I'm not going to discuss about this because I'm already late on time, I suppose. But what we do is that we have a topological singular set now. There's some sort of operator which is defined on the Sobolev space, W1P. Here I am assuming that P is, let's say, strictly greater than K minus 1, and let's say strictly less than K. I am defining, we could define an operator defined on this Sobolev space with values in the set of flat chains with coefficient in the group that I have defined so far. It sort of characterized the topological singularities of my map. For instance, if my domain here is a subset of Rk, to make things simple, and if U turns out to be smooth or continuous, at least, in omega except for a finite set, so let's suppose that in addition to being a Sobolev map, U is also continuous except for a finite set of points. Then, you could take a small ball, which will be a small ball surrounding the first singular point, and you could look at the homotopy class of U on the boundary of such ball. I call it gamma 1, for instance. Of course, the homotopy class will be the same if you look at a slightly bigger ball, so long as the ball only contains the singular point A1. Because the definition of homotopy is made precisely to be invariant in such sort of situations. And in this particular case, your operator would be of the form a finite combination of the points, basically, the singular points, weighted by multiplicity that corresponds to the homotopy classes of U around each singularity. So now this would be, of course, only a very, very specific situation because you're assuming that U has a very specific form. But actually, it turns out that you can, well, for instance, it actually turns out that maps with this sort of regularity are dense, in the Sobolev class that I have in here, at least if the dimension of the domain is equal to K. And therefore, you could define your topological operator S by a density argument. It has been done. And you could perform the same construction in greater dimension too. It's a bit more complicated. In fact, there's some level of complications hidden in here, but it has been done. This was done by Paxade and Rivière. I believe it was 2003, under some additional technical restrictions, and then later on it was generalized by yours truly and Giandomenico Orlandi, and I believe the year was 19, the year the paper was published, I don't remember. So the construction, I won't get into the technicalities of the construction because it would take time, and my time is almost over. I just want to state finally the main result, because I have all the ingredients that I need now. And as promised, I'm going to state a convergent theorem just for minimizers. But if you prefer gamma convergence, you could do that as well. And we have a gamma convergence statement which is inspired by Alberti Baldorlandi. 05, so Abo 2, the second paper by Alberti Baldorlandi, sorry. That one, the gamma convergence for the Ginzburg-Landau problem. We could do something similar in here, but I just want to state the theorem for minimizers. And it goes as follows. Suppose the operation is single-valued. Which is the technical restriction I was mentioning before. I'm not still able to do to prove and state even a result that works for any target manifold because I need to consider flat chains, and what we have so far is only flat chains with coefficients in a group, and the group usually has to have a single-valued operation on it. So this is my technical restriction. So suppose the operation is single-valued, and let UP be a minimizer of the p-Dirichlet integral in the set W1P with boundary values given by G. Again, G is supposed to be, I wrote it before, but I just as well write it again, in the trace space for the K problem. Then, up to extraction of a subsequence, you could consider the singular sets defined in such a way and you could extract a subsequence that converges in the flat norm to some limit. And the limit is not just any chain. The limit is a minimizer of the mass. So it's area minimizing in a sense. It's not quite area minimizing because we have coefficients as well. So it minimizes some sort of weighted area functional, which is the mass of a flat chain, with coefficient given by this norm on my group. So this is a minimizer of the mass in its homology class. And moreover, the limit as p tends to k from below of a normalization factor times the p-Dirichlet energy of up, this is precisely equal to the mass. Sorry. Having chosen the norm in such a way. Typically for gamma convergence results or results of that type in the Ginzburg-Landau literature, there's going to be some sort of normalization constant in front of the right-hand side. Here there is no normalization constant, it's equal to 1, but this is because the constant has been embedded already in the definition of the norm. So you don't see any constant in here, but there is a constant, well, several different constants actually embedded in the definition of the norm. And how much time do I have? Probably. So probably this is just a point where I should stop, and I thank you all very much for your attention and your patience that you have suffered through this.
Thanks. Are you able to somehow conversely prove that for any minimizer, for any minimizing chain, you can reach it as a limit?
Yeah, I mean, yes, it's a gamma convergence statement actually. So what we can do, well, I've hidden a couple of details actually. There's a sort of class of admissible competitors for the limit problem. So I said that S star is a minimizer of the mass in its homology class, which is true. What I haven't said is that the homology class is also uniquely defined by the boundary value and the domain. So if you give me any finite mass chain of the appropriate dimension in that homology class, any finite mass chain in that homology class, I can find a sequence of competitors so not necessarily, it's a gamma convergence statement. So I can find a recovery sequence of maps that converge to that particular chain with convergence of the energies.
In this case, it doesn't even need to be a minimizer, right?
No, I mean, no, it doesn't even have to be a minimizer. You just give me any admissible competitor, admissible in terms of topology, and then you can construct a recovery sequence that goes to that competitor.
Okay, but then if you take a current which is minimizing it in this prescribed class given by the boundary datum, can you achieve it with a sequence of minimizers of the problem? Or this is open? Or you have reason to believe that it's not possible?
If you mean minimizers such as in local minimizer of the mass, perhaps with typically, I don't know, I haven't thought of it, but typically that sort of things are easy to do when you have some sort of non-degeneracy, right? That you're an isolated minimizer and that sort of thing. But then again, you might not expect to have some sort of strong non-degeneracy assumption because perhaps your problem has some sort of symmetries, and then you need to make sure that you construct something that goes the right way. I don't know. I haven't thought of the details. It's a standard gamma convergence. I haven't thought of that particular question. It's just a gamma convergence approach. The standard gamma convergence result. In the Ginzburg-Landau setting, they're doing that sort of results right now, right? Contreras and Stenberg and other people afterwards. including, for instance, Pigatti and the Pigatti said De Filippis and Pigatti very recently, but that was not for the limit as p goes to k. It was for the standard Ginzburg-Landau functional. It's a different limit, but they are studying that sort of problem right now. So, and it's for general critical points. Yes, it's for general critical points, not necessarily minimizers or.
Thank you.
Thank you. I can also be just down, yeah. But I think it's for the purposes of the recording.
For the recording. Okay, all right. So you mentioned that your operation plus,
yes,
you need to assume it to be single valued. So
yes.
when is it? It is not single valued. So which kind of restrictions do you get on your target manifold if you assume that?
Well, quite heavy restrictions, to be honest, because, for instance, if you look at surfaces, compact closed surfaces, so without any boundary, in dimension 2, and let's say we're looking at orientable surfaces. So there's a sphere, good. There's the torus. The fundamental group is Z over Z2, and gamma n is going to be Z2 as well. All other orientable surfaces, closed surfaces in dimension 2, have non-abelian fundamental group, which means the gamma here would have a multi-valued, non-single valued, not single valued operation. And we don't know what to do in that case. There are other examples that I was mentioning before biaxial nematics. In that case, the manifold, the relevant manifold, would be a quotient of the rotation group with, I don't know how to call it, with respect to the group of symmetries of a rectangle, which, if I'm not mistaken, is the Klein 4 group. And in this case, well, the fundamental group actually is not quite this one, because it's a product of this one with a group of order 2, but it's a non-direct product. So long story short, the fundamental group would be a non-abelian one. It's the unit group of quaternions. Sorry, I got a bit carried away by inflation. And then this one again is the set of conjugacy classes in this group in this quaternion unit group, and the product is multi-valued again. And this is quite interesting for the application purposes, at least in terms of applications to a material that has never been observed. But more generally, in material science, it's fairly common to have quotients of the rotation group with respect to some sort of isotropy groups, which describes the possible orientations of. Because the quotient group then describes the possible orientation of a polyhedron or something that perhaps describes the molecular symmetry or so. And when you start doing that sort of things, it's fairly common to have non-abelian fundamental group and therefore a multi-valued operation on gamma. So it's still a bit disappointing, to be honest, that I am not that we cannot cover the multi-valued case. There is a result that does carry over to the non-abelian fundamental group, where there's a few results that cover the case in which your dimension is two-dimensional, in which case your singularities are just points, and then even if you don't have, a description in terms of geometric measure theory, it's points. So you can play around with those. But there's an interesting result in which the domain is 3D, and the singularities that you see are lines. And there, it's a result that is due to I'm mispronouncing, Boulagny, Van Werenberg and Van Schaftingen and Van Werenberg, sorry. they're doing something similar in a slightly different limit. It's sorry. It's really the p goes to 2 limit. They're not looking at gamma convergence, only at minimizing. But they're able to cover also the case in which the manifold has multi-valued gamma, so to speak. But then again, it's only the dimension 3, and that's again because in dimension 3, the singular sets that you expect to see are lines. In fact, straight lines, segments, because of minimalities, and then you can describe them by hand, such a way, in a manner of speaking. You don't need geometric measure theory to describe them. Otherwise, I'm lost.
Okay, so thank you very much for organizing this event and also for inviting me here and for giving me this opportunity to give this talk. So as you said, I'm currently a postdoc at ETH Zurich under supervision of Tristan Rivière, and previously from 2022 to 2024 I was doing my PhD in Lyon under supervision of Petru Mironescu. And my goal for today is to give an overview of the topic I've been working on during this PhD, which is those approximation problems for Sobolev maps to manifolds. So I don't want to focus on a specific result or anything like that. My goal is really to give a broad overview of this topic, kind of its history, some important binohistorical results, and also to explain briefly some recent contributions, but no technicality, I promise. And I guess this was made on purpose, but it will somehow resonate with the talk that we've just had. There will be like a lot of similarities. Okay, very well. So first, let me define the framework that we are going to work with. Nothing very different from what was before. So I will consider N to be a smooth compact Riemannian manifold that I can assume without loss of generality to be a subset of some sufficiently large Euclidean space. Here there's a slight difference that I'm allowing my domain to be a manifold, not necessarily an open set. The dimension will be denoted by small m. But if you don't like maps defined on manifolds, you can always think of M to be the closure of the unit ball in Rm. What's important in this field is that the target is a manifold. But all the problems that I'm going to talk about are already interesting in the model case where the domain is like a unit ball. So if you don't like domains being manifold, just think that M is a ball. And as usual, there is an integrability parameter between 1 and plus infinity, and a regularity parameter between 0 and plus infinity, which need not be 1 or even an integer. So I'm allowing for higher order or even fractional spaces. And then the object that we want to focus on is this Sobolev space of WSP maps from M to N. And since our target is embedded, it's really easy to define. You just define it as all those Sobolev maps from M to R nu. So these are classical vector-valued Sobolev maps, so Sobolev map component by component, that respect this additional restriction that they should take their values into the prescribed targets almost everywhere. So the manifold is really just a constraint on the values that you're allowing for your maps. And even though this is not the topic of my talk, I want to briefly explain why people do care about these objects. Of course, they are nice to study per se, and they raise at least according to my opinion, very nice and challenging problems. But they also tend to appear a bit everywhere in problems with a geometric flavor. Like, for instance, one of the first instances where they appeared is in the study of harmonic maps between manifolds, such as in the previous talk. Here I'm just giving a list which is really not exhaustive, just a few people that started to work on this already in the early 70s, I believe. Then also, in connection with numerics, these maps appear when you want to encode the attitudes of a square or a cube in computer graphics, for instance. So imagine that you want to mesh a surface or a volume for some kind of computer graphics or finite elements method or anything like that. then you want to know at each point in which direction your square or your cube is oriented. And for doing so, it's natural to look at maps with values into the circle or the sphere or some group of rotation to prescribe the direction. And again, you are back to maps with values into a compact manifold. I'm just giving you one paper for cubes, and here there is this extreme project, which was an ERC project run in UC Louvain in Belgium about finite element methods, and that really used like mappings to manifold at some point. More recently, there has also been some incentive to use those objects to study heterogeneous materials, notably ferromagnetism theory. Once again, a few names that I've seen recently appear in the literature. And I would like to emphasize that in these papers, they are really using the techniques that are developed to study those abstract problems on maps to manifolds to get results in this direction. And this somehow is one more instance of a saying that I like, which is that in analysis, what's important is not quite the results, but more the techniques that you can like reuse and reapply to get new results. And of course, many more, Ginsburg-Landau, Coursera materials, and so on and so on. But as I said, this is not the topic of this presentation. What I want to speak about is the approximation problem. And here is the base problem, the strong approximation problem. So the starting point is this very well-known result that if you take a Sobolev function with values into R, you can always approximate it with a sequence of smooth maps. And this does not only tell you more about the structure of the Sobolev space, that it's actually just the closure of smooth maps. It's also very useful in practice because most of the time, if you want to prove a property for Sobolev maps, what you want to do is first to prove it for smooth maps where you can much more easily justify all your computations, and then transfer it by a density argument to all the Sobolev space. And you might be willing to do the same for mappings to manifolds. So you might be willing to say, okay, let me start with smooth maps from M to N, which are defined as in differential geometry. Let me put the Sobolev norm on them, and let me take the closure. And I get this space, which I call HSPS, S for strong. And the question is, do I get my Sobolev space? So do I recover this Sobolev space WSP that I defined via the embedding if I do so? And let me just emphasize that you cannot answer yes to this question just by saying, let me apply this component by component, and not even the proof, because how is the classical proof of this result? It's by convolution. Like you convolve your map and you prove that the convolution goes to the original map when you let the parameter go to 0. But the problem is that convolution, it is morally just a convex combination, and this is not compatible at all with the constraint induced by the manifold, which is in general non-convex. Like for instance, even already if N is a sphere, you take convex combination of points in the sphere, you are no longer in the sphere, too bad. So you cannot answer positively to this question, not even by applying like easy modification of this of the proof of this. But you might be thinking, okay, still density of smooth maps is something reasonable. We should just find another proof of this, which will carry on to this setting. Unfortunately, the answer is no. It's really an obstruction. It might happen that some Sobolev maps into a manifold cannot be approximated strongly in the Sobolev norm with smooth maps. And to the best of my knowledge, the first example of such an obstruction was exhibited by Richard Schön and Karen Uhlenbeck in 1983. And it's this map, which is called the hedgehog, X over mod X, which goes from B3 to S2. And what they prove is that, obviously, it's in W1P when P is less than 3. And if, moreover, P is bigger than 2, then this map cannot be approximated with a sequence of smooth S2 valued maps. And I want to sketch the proof of this because I think it's quite highlighting of what's going on here. Oops, there was a step. So the proof is by contradiction. Is it big enough? Yes. Okay. So you assume that you would have a sequence UN of smooth maps going from B3 to S2, strongly converging to U0 in W1P. Okay? And now you use an argument which is very widespread in this area, which is called the genericity argument. So I said that I would avoid technicality at all costs, and this is a good restriction. It means that I cannot show a proof which does not fit on this blackboard. I think it's going to be okay. So up to extraction of the subsequence, which I'm not going to write, I get that for almost every R in 0, 1, I have the same convergence on the sphere of radius R centered at the origin to U0. This is no magic, this is just Fubini-Tonelli. You write that the Sobolev norm on B3 is the integral of the norm on the sphere when the radius goes from 0 to 1. And now the question is, what have I gained by doing so? Well, now I'm on a 2D domain, and my P, I assumed it to be bigger or equal than 2, so I have more a Sobolev embedding. Which means that this convergence is uniform. But now, these maps, by their very definition, they are the restriction to the sphere of smooth maps in the closed ball, which is bounded by the sphere, which means that they are null homotopic. You get a homotopy from this map to UN of 0 just by reading the values on the smaller and smaller spheres. So these maps, they are homotopic to a constant. On the other hand, this map, by this construction, it is morally just the identity from S2 to S2, which is a degree 1 map, which is not null homotopic. So I would have proved that I have a sequence of null homotopic maps converging uniformly to a non-null homotopic map, and this is not possible because homotopic classes are preserved through uniform convergence. So this is a contradiction. And there are two very important features of this counterexample that I want to emphasize. The first one is that this counterexample itself, it's not smooth, obviously, but it's not very far away from being smooth. It's smooth outside of one point singularity, which is at the origin, and which is where the problem happens. And the second feature is that the abstraction to the approximation comes from the fact that this map realizes around its singularity a map from S2 to S2, which is not homotopic to a constant. Or in a more technical way, it realizes a non-zero element of the homotopy group of S2 of order 2. And this is why there is an abstraction. So we're going to put these observations aside for a moment, but they will come back very importantly soon. So once you're faced with this fact that smooth maps need not be dense in the Sobolev space, you can ask yourself a series of questions, among which these 4 questions. The first one is, okay, can I at least characterize those values of the parameters, so S, P, M, and N, for which I have this strong approximation property, if any? Or maybe I'm ready to give up on smooth maps, and I just want to find a suitable class of almost smooth maps, which would always be dense in the Sobolev space. Or maybe I'm ready to give up on approximating all my maps, and I just want to know which maps I can approximate. So in other words, if I can characterize this closure of smooth maps HSPS. Or finally, maybe I really want to approximate all my maps with smooth maps, and then I have to give up on strong convergence. Maybe I'm just demanding too much. And I can wonder what would happen if I would replace this strong convergence with a weaker notion. And these are the 4 questions that I want to briefly talk about, to give an overview about. But before, let me do a small digression to explain an assumption that will be popping out during essentially the whole talk. So you will always see the assumption that SP is less than M in my statements. And this is because when SP is greater or equal than M, then like the slogan is essentially that everything goes as in the real valued case. And in particular, the closure of smooth maps is always a whole Sobolev space when SP is bigger or equal than M. This was essentially contained also in this work by Schoen and Uhlenbeck. And I'm not going to give the whole proof, but it's essentially just, once again, this Morey-Sobolev embedding, because like apply the classical approximation theorem component by component, you get a sequence of smooth maps converging to your map. Since you did not care about preserving this constraint, they are only valued into the ambient space. But since you have Morey-Sobolev, they are converging uniformly to the target, which means that at some point they are uniformly close to the target manifold, and then you can reproject via the nearest point projection, which always exists as you have a compact target, and then you get your approximation with smooth n-valued maps. Okay, in the limiting case, you don't have embedding into C0, you have embedding into VMO, but even though this doesn't give you uniform convergence, it can still be proved by a bit more work that it gives you uniform convergence to the target manifold. At some point, you're not uniformly close to the target map, but you are uniformly close to the target manifold still, and you can once again reproject. And this is very well explained in this work by Brezis and Nierenberg about VMO spaces into manifolds. So for now on, we are going to focus on the non-trivial case where SP is less than M. So first, I want to speak about this so-called strong approximation problem, which gathers together questions 1 and 2, which you will see are strongly connected to each other. So before we look together at this scary definition, let me remind you the first important feature of this X over mod X counterexample that we saw. I told you that it is smooth outside of a point singularity. And so we are going to define a class of maps which look like this hedgehog map. So we define the class R, Ri, as the set of all maps from M to N, which are smooth outside of a singular set, which obviously depends on the map itself, for which we require that first it is a union of I-dimensional submanifolds, and second we require some control on the rate of blow-up of the derivatives when you are approaching this singular set. This is just to ensure that this class is contained in the Sobolev space in which you want it to be contained. In particular, if you take I to be 0, then you get zero-dimensional submanifold singularities, or in other words, point singularities. And in particular, this hedgehog map is in the class R not. But of course, you can also, like by varying this parameter I, you can go for maps with line singularities, curve singularities, surfaces singularities, or anything that you want to think about. Okay, very well. And so somehow this counterexample, once again, it belongs to this class R, and also it arises because of the non-vanishing of some homotopy group of the target. And now there is this very beautiful theorem which is due to Fabrice Betuel in 1991 in the model case where S is equal to 1, so W1P, which somehow tells you that these are the only two things that can go wrong. These are the only enemies to the strong approximation property. So more precisely, you have the strong approximation property if and only if this homotopy group of the target of dimension integer part of the integrability parameter is trivial. Or in other words, if any map from S, the sphere of dimension integer part of SP to the target manifold can be extended inside the ball that it bounds. And in addition, the class of maps that are smooth outside of a singular set of dimension m minus integer part of p minus 1 is always dense in the Sobolev space. And let us do a quick sanity check. If we take B3 to S2, we have m equal 3, integer part of p is 2, so this is 3 minus 2 minus 1, this is 0, so this is the class R0. And the pi 2 of S2 is non-trivial, which is why we don't have the strong approximation property. Let me just mention that some partial cases, mostly for sphere-valued maps, were already known by joint work of Fabrice Betuel with Xiaoming Zheng 3 years before. And also, very importantly, you might think that I'm tricking you, because here my domain is just a ball, while before I've always been writing statements for general domains. This is not by mistake, this is on purpose, because if the domain is allowed to be arbitrary, it might happen that the topology of the domain will interact with the topology of the target to create additional so-called global obstructions. They are global because they take into account the whole topology of the domain, and you don't see them if the domain has no topology, such as a ball. And this was understood by Hong Fenbo and Lin Fanghua in 2003. There's also the density of the class R. This doesn't change. And there's also a necessary and sufficient condition for the strong approximation property to hold. It is just that it's formulated in terms of an extension property, which involves both the domain and the target, which is a bit more cumbersome to state. So I wanted to omit it, but if you are interested, I just refer you to this paper. And of course, this condition comprises this and reduces to it when the domain has no topology. So this was for S equal 1, and as you may expect, there was a lot of effort to try to push this result further to other values of the regularity parameter. In particular, there was a lot of effort to get it for like trace spaces, fractional Sobolev spaces with S between 0 and 1. And the final stone was laid by Haim Prezis and Petro Mironescu in 2015, after a numerous amount of important partial contributions by Fabrice Betuel, Tristan Rivière, Pierre Bousquet, Domenico Mucci, and Bousquet, Pons, van Schaftingen, in many specific cases with additional assumptions. In parallel, the case of higher order integer Sobolev spaces, so W2P, W3P, and so on, was completely solved by Pierre Bousquet, Auguste Pons, and Jean van Schaftingen the same year in 2015. And my contribution to this problem was to settle the general case, so the missing case, S larger than 1 non-integer, for which some partial results were already known, if the target is a sphere by Miguel Escobedo, and a bit more generally if the target is integer part of SP connected by Pierre Bousquet, Auguste Pons, and Jean van Schaftingen. And so now you can state this theorem in full generality. So let any parameter P between 1 and plus infinity, let any regularity parameter S between 0 and plus infinity. You have this strong approximation property if and only if this homotopy group of order integer part of SP is trivial, and this class R of almost smooth maps is always dense in the Sobolev space. And the argument can be transferred to also handle the case where the domain can have non-trivial topology, and you get exactly the condition that you would expect by generalizing the condition that was exhibited by Hong and Lin. I'm of course not going to explain the proof, but I just want to comment a bit on the difficulties that you are facing when you are trying to move from W1P to W some integer P to W some non-integer larger than 1P. So the method by Betuel is this so-called technique of good and bad cubes. So you cut your domain into a grid of cubes, and then you look at the good cubes, which are the cubes where your map does not oscillate too much, and on these cubes you can do convolution. And then you have the bad cubes where your map can do anything very bad, but there are not too many bad cubes, so you don't need to be very careful on the bad cubes. And then you do something on the good cubes, you do something on the bad cubes, and if you sweat a lot, then you get your approximation. And so one of the difficulties is to be able to glue together the constructions on the different cubes. So if you are doing W1P, if you want to glue two constructions on two neighboring cubes, you just need to make sure that the traces coincide. And then you have a W1P map on the union of those cubes. But if you want to do W2P, then it's not sufficient. I mean, maybe you have broken the derivative and this is bad. So you need smoother constructions which will preserve more and more derivatives to gain in order. And this was a challenge that Pierre Bousquet, Auguste Pons, and Jean-Vas Raftingen had to face. And for this, they needed to introduce and develop quite a bunch of new tools suited for this higher rigidity of higher order Sobolev spaces. And then if you want to move to the fractional setting, you have to cope in addition with the non-local character of the Gallardo seminorm that defines fractional Sobolev spaces. And so what I had to do was to take this technique of good and bad cubes by Betuel, take these like smoother tools developed by Pierre Bousquet, Auguste Pons, and Jean-Vas Raftingen, and show that you can adapt them suitably and provide them with also the non-local estimates for the Gallardo seminorm to show that this same general scheme of proof can be applied to get the strong density also in higher order fractional Sobolev spaces. And on the way, the argument like works for the whole range S between 0 and plus infinity, including S less than 1, which was, as I said, obtained by Bresis and Mironescu with a different approach. So this gives also like a unified approach that covers the whole range of the regularity parameter. So that was it for this strong approximation problem. By the way, I forget to say, but if you have any question, as in the previous talk, feel free to interrupt me at any time. So no question until now? No? So let me move to question 3, which is about characterizing the closure of smooth maps. And more precisely, I want to focus on what are called analytic characterizations. So what I want to do is to be able to take any Sobolev map with values into a target manifold and define an object that I can compute for this map. It gives me maybe a number or maybe something more complicated. And just by looking at this object, I can tell if my map can be approximated or not. So let us go back to a safe place, W1 to B3 to S2. We know that there is no strong approximation property, that this hedgehog lies into this space. And in this context, there is a very promising object, which is called the Jacobian. So let's decipher this together. So we take the volume form on the target, the sphere. We have our map U, which goes from B3 to S2. So we can pull back the volume form on B3 to get a 2 form on B3. So this is this U sharp of omega S2. And by the way, so since this is a 2 form, the pullback involves products of 2 factors of derivatives of the map U, and since U is in W12 by Hölder, this makes sense as an L1 map. And now you have a 2 form on B3, so you would like to take its differential to get a 3 form on B3 that you can integrate, because you can only integrate 3 forms on B3. Problem, I said that this is just L1, so you cannot take the standard differential, but you can take the differential in the sense of distributions, and this is exactly the definition of the Jacobian, so you can test it against any smooth, compactly supported test function, and it gives you this expression. To the best of my knowledge, this idea of considering the Jacobian in the sense of distribution goes back to the work of Sir John Ball in 1976. And I will not try to explain why one is willing to do so, like where does this idea come from? I don't even know. Instead, I'm going to try to convince you that it's indeed the right object to work with by computing the Jacobian of this hedgehog map. So once again, one blackboard computation. So I start with something very easy. I start with Leibniz rule. So if I have a smooth map, then I can compute this. Just apply Leibniz rule. So the D falls on the first factor first. And then the D falls on the second factor. There is a sign that I don't want to remember. Up. And now, since I said that my map is smooth, the differential commutes with the pullback, so I can put this inside. The volume form on S2 is closed, so this is 0, so this goes away. And so I just get this, which is, as you may recognize, the integrand in this expression. So in other words, the integrand here is an exact form. And now I want to take profit of this and to apply Stokes' formula, but once again, I need my map to be smooth. You cannot exchange the differential and the pullback if the map is not smooth. So I need, for this hedgehog map, to remove a small disk around the origin, which I'm going to do. So by just dominated convergence theorem, I have this. So I remove a ball of radius epsilon, and then I can use this formula. So my integrand is this. I apply Stokes. So I have the integral of a d, so it's the integral of this on the boundary. I have no exterior boundary because my form is compactly supported, so I just see the inner boundary. The boundary of the ball of radius epsilon of alpha wedge u sharp omega. Now I'm cheating a bit. This is smooth, so when epsilon is small, it's essentially alpha of 0. I get this. So let me be a bit sloppy. And now, since this is just, forgot the knots everywhere. Since this is just x over mod x, this pullback is just rescaling the volume form to the small ball. So by change of variable, I get that this is alpha of 0 times the integral on the unit sphere of just the volume form. And because it's the volume form, this is the volume of the sphere. So this gives me 4 pi times alpha of 0. And since this is valid for any alpha, this tells me that, surprise, the Jacobian is 4 pi times the delta Dirac at 0. So in other words, it tells you, hey, there is a singularity, and it lies exactly here. It lies exactly at the origin where the mass is concentrated. And you can do the same computation for any map of the class R0, and you are going to get a sum of Dirac delta at the singularities, and the weight in front will be 4 pi times the degree of the map on a small circle around the singularity. So it's not only telling you where the singularities are, it's also telling you how much they weigh somehow with respect to the pi 2. On the other hand, if I had started with a smooth map, then I would not have needed to remove this small ball, so I would have gotten 0 directly here. And since the Jacobian is obviously continuous with respect to the W12 convergence, this extends to the closure of smooth maps. So in other words, this Jacobian vanishes on the closure of smooth maps. So once again, I have an object that vanishes on the closure of smooth maps, and that is something on maps with singularities. And this leads, after a proof, to the theorem of Fabrice-Bethuel in 1990 that, as you might expect, the closure of smooth maps is exactly those maps whose Jacobian is 0. So we have our analytic characterization of the closure of smooth maps when we are in W12 from B3 to S2. So of course, now we want to push this further in more generality. Here are some examples of research in this direction. One important step is this result by Fabrice-Bethuel, Jean-Michel Coron, Françoise de Mangel, and Frédéric Hella in 1991, which works in any space W1P when you have this assumption that I won't explain in details, which is that the cohomology of the target sees the important homotopy group. So in other words, you can compute the pi p just using differential forms. This is what this assumption means. And in this case, you can also like define a Jacobian, and you have a family of Jacobians, one for each form. So replace omega s2 by any form omega. And if all these objects vanish, then your map can be approximated with smoothness. This is an if and only if. And this was extended very recently in the preprint that came out at the beginning of the year by Pierre Bousquet, Gustave Pons, and Jean Skaftingen to high-order integer Sobolev spaces. In the same line of research, there is the whole theory of Cartesian currents by Giaquinta, Modica, Soucek, and collaborators to try to define the singular set of a Sobolev map as a Cartesian current using the language of geometric measure theory, also with the hope that a map would be approximable if and only if its singular set is zero as a current. Then there is also, as was explained in the talk that we've just seen, this approach by flat chains with values into the homotopy group, which, as was just said, has been initiated by Paxad and Rivière and pursued by Canevari and Orlandi, and which is, to the best of my knowledge, the only approach that is able to deal with torsion. So you need this condition that was just presented, that all the previous homotopy groups have to vanish, but you can afford that the pi integer part of P has torsion, which this cannot afford. And there is also the theory of scans by Hard and Rivière, which doesn't need this assumption that all the previous homotopy group vanish, but it can only deal with rational homotopy groups, so you cannot do it if the pi P has torsion. So as you see, not everything is settled. Like if the pi P has torsion and also some previous groups do not vanish, then nothing of this, to the best of my knowledge, will apply. And also, a common roof above all these results is that they are for W1P, with a small exception of this, which is for W2, 3, and so on P. But there's nothing in this list for WSP s less than 1, and this would be the next step. But then there is a very first difficulty in defining this, because if you take u in W, I don't know, 1/2 2, then you don't have even a full derivative, so you cannot even make sense of this as an L1 function. And it turns out that there is a very nice idea to do this, which is, again, just Stokes' formula. So let me start with, again, a map from B3 to S2, not very regular. I mean, the goal is to take it in some fractional Sobolev space. I take big U. Okay, now I will change the letter because my U's are not very easy to distinguish. So I extend it as a map. So I view this as the boundary of a cylinder, and I extend it. So you can do this via convolution, for instance, like classical extension of traces. It's just that then you don't go in the target manifold, you go in the ambient space, but this is not a problem. Your test function, you also extend it on the same space. And obviously, omega S2, you can view it as a two form on R3. Like you just take the expression of this, and this gives you this extend naturally as a two form on R3. It's just that it's no longer closed. It's closed as a two form on S2, but it's not closed as a two form on R3. And actually, the differential of this is going to be the volume form on R3 up to some constant. And now you compute the Jacobian. So once again, it's this integral d alpha wedge u sharp omega S2. Now you use Stokes' formula, but the other way around, you view this as a boundary. And so you get this, and you put in all the extensions in the machinery. D alpha tilde wedge v sharp omega S2. You distribute the differential, so here d of d is 0, so you don't see this term. Up. And as far as I remember, there is a minus sign. I'm very bad with minus signs. So you put the differential there, you move it inside. Oops. And you get this.
And now all of this makes perfect sense because this is smooth, this is smooth, this is smooth, everything is smooth, you are happy. So now the strategy to define the Jacobian of fractional Sobolev maps is quite clear. Prove that this computation, which at this stage is just formal, I just apply Stokes' formula without checking any assumption. So prove that this computation is rigorous when U is in W1P. Then prove that this guy still makes sense when U is in WSP as less than 1 and is continuous with respect to the WSP norm. So this will show that this is the unique extension by continuity of this on the larger space WSP. And then hopefully, if you have enough topological assumptions on the target, you can prove that this object will characterize the closure of smooth maps. And this is something we were able to achieve with Petru Mironescu and Xiao Kai at the beginning of this year. So I'm writing a sloppy statement, which is that without assumption, if you have a form, you can apply this procedure, and this will define an associated Jacobian which extends by continuity the Jacobian for W1P. And in addition, if you have this nice assumption that the cohomology of the target detects the homotopy, then these Jacobian will characterize the closure of smooth maps. And obviously, this is not the first result in this direction. Actually, this very nice idea that I sketched at the blackboard, it's due to Jean Bourgain, Brezis, and Petru Mironescu in 2005 to define the Jacobian of fractional Sobolev maps for sphere-valued maps. Then this was pursued by Pierre Bousquet and Petru Mironescu, who studied further properties of this Jacobian. And then recently, Domenico Mucci, he used this object to state characterization of the closure of smooth maps, once again for sphere-valued maps. And so somehow what we did was to carefully explain all the setting and the machinery to be able to define this object for a general target manifold and to prove that under this assumption that the cohomology of the target detects the homotopy, the objects that you get characterize the closure of smooth maps. And now with the 7 minutes that I have 7 minutes, right? So with the 7 minutes that I have left, I want to speak a bit about the last topic, which is the weak approximation problem. So once again, you say, okay, I really want to do approximation of everything with smooth maps. I don't want to give up anything. So the only thing that I can give up is the strong convergence. So let us look instead at the weak convergence. So we write with this customary harpoon notation that the sequence weakly converges whenever the energies of the gradients remain bounded along the sequence, plus the maps converge almost everywhere. So you give up on strong convergence in norm for both the functions and their derivatives. You just ask that the derivatives are bounded, plus a very weak notion of convergence at the level of the functions themselves, just to be able to identify uniquely the limit. This is just why you want to do this. You can do almost every convergence. You can also do convergence in measure, in L1 lock, any weak convergence that you wish. And then you define H1PW, W for weak, as all the weak limits of smooth maps. And you ask the same question. Do I now recover the whole Sobolev space? So this is obviously a larger space than H1PS. So do I get the whole Sobolev space? Before answering, let me just make 2 quick comments on this definition. First, if you are used to linear problems, you might be wondering what's the connection between this and the linear notion of weak convergence induced by the dual. Well, they are equivalent when P is bigger than 1. This is just like compactness and reflexivity of LP spaces. If P is equal to 1, then you don't have reflexivity of L1. This is a bit painful, and actually this notion is strictly weaker than the usual weak convergence. If you want to recover weak convergence, you need to assume that the derivatives are uniformly integrable along the sequence. But the advantage of working with this is it's a somehow intrinsic notion. You don't need to know how the manifold is embedded to get the linear notion of weak convergence induced by the ambient space. And it's not even clear that this notion does not depend on the embedding, while this doesn't depend on the choice of embedding. And second, okay, it's very nice to weaken the notion of convergence. Still, you need to work with something which is sufficiently strong so that it is meaningful. Like you don't want to say that you just work with almost everywhere convergence, because you can do nothing with this. And it's true that this notion is still sufficiently strong so that you can pass to the limit properties by this notion of convergence and stuff like that. So there's the first bad news for our question, which is that if p is not an integer, then we've changed nothing. We've tried, but we didn't achieve anything. Actually, you have the same abstraction to the weak approximation property as you had for the strong approximation property. And it's even more dramatic, as shown by this theorem of Fabrice-Bethuel, once again, that both spaces H1PW and H1PS are the same. So you really gained nothing by moving from strong convergence to weak convergence. But there is this assumption that p is not an integer, and when p is an integer, there's something new going on. In particular, if you take p integer and weak convergence, now you can approximate this hedgehog map x over mod x. And it's not an isolated phenomenon. Actually, it comes from the fact that you have the weak approximation property in W12 from B3 to S2, even though you don't have the strong approximation property. So you really gain something when p is an integer. This has been extended by Piotr Heiwash for p-1 connected targets. So just quick comparison, for strong convergence, you would need that the homotopy group of n of order p is trivial, since p is an integer. Here you say pi p can be anything, but in exchange, all the previous groups have to be trivial. So this is still quite demanding as an assumption. It's the same assumption as in the previous talk. Also, in particular, if p is equal to 1, then this condition is empty. So this means that you have always the weak approximation property W11. It was slightly extended by Paxad and Rivière, who devised another method of weak approximation that recovers Heiwash result when p is equal to 2, and which also applies to some non-simply connected target to which the result by Heiwash would not apply. And one last result, which is that in W22 from B5 to S3, which doesn't fit the framework of any of these, you also have the weak approximation property. So you see, like, you have positive results piling up, and people were believing, okay, it's just a matter of working harder, and we are going to be able to prove that the weak approximation property always holds when p is an integer. And then came this groundbreaking counterexample by Fabrice-Bethuel, showing that the weak approximation property fails in W13 from B4 to S2, even though 3 is an integer. Okay, to tell you the whole story, some abstractions were already known. There was those global abstractions, again, by Hong and Lin, but they only apply, as I explained, when the domain has topology. So these would not apply in a ball. So this is the first example of an abstraction to the weak approximation property when the domain is a ball and when p is an integer. And this is quite difficult as a result. I mean, the paper is 130 pages for constructing the counterexample. And it involves tools such as the Pontryagin construction, the Hopf invariant, the theory of scans by Hard and Rivière, and also branch optimal transportation. So a lot of tools gathered together to get this result. And it's restricted to p equal 3. And what we were able to do with Jean was to prove that for any integer p, there's a target for which things might go wrong, as in Bethuel's counterexample. So for any p integer, there's a target for which the weak approximation property does not hold in W1p, except for p equal 1, because it always holds, as I said. And the target is explicit. It's a bit complicated. It's essentially a p skeleton of a torus of dimension p plus 1. So it's explicit, but it's not very simple. So maybe you might be unhappy about this. I once gave this talk just after a talk of probabilities with values into the sphere, and there was a question, can you do it for general manifolds? And the speaker replied, I don't like manifolds. So maybe you are, as the speaker, you don't like manifolds except sphere. So here is another good news for you, which is that you can also do it for spheres. Not for every parameter P, there are restrictions, but we can do it for W1 4D minus 1 into S2D. So in particular, if you take D equal 1, you have W1 3 into S2, so you have Bethuel's counterexample. So this shows that Bethuel's counterexample is actually part of an infinite family, and those values are such that you have a Hopf invariant from S4D minus 1 to S2D. So each time you have a Hopf invariant, you have an abstraction. This is what is hidden behind this. Yes? Yeah, for every manifold, yes. So you can already take M to be a ball. And then once you get it for a ball, you get it for everything. And I'm not going to explain how it's constructed. I just want to say that at the core of the construction, there's nothing more difficult as periodic maps. We're just doing like periodic maps. For the sphere, we do periodic maps on a grid, which are constructed by the white-hat product of maps on the faces of the grid, and you get maps with degree 2 singularities on each cube. And for the first family, we do a periodic quotient into the P skeleton of TP plus 1. And for each family, we need one estimate to show that there is no weak approximation. For the first family, it's just the isoperimetric inequality. And for the second family, it's Riviere's estimate on the minimal energy that you need to realize the Hopf invariant. So once again, here there's a lot of open problems remaining. Like we have shown that things can go wrong, but it's still very far away from being a whole characterization of when does weak approximation hold or not. So yeah, plenty of open things to still be explored. So that's everything I wanted to say. I thank you very much for your attention, and if you have questions, feel free.
Well, thank you very much for this very nice talk. And then going back to this last, or the penultimate, well, the last two results, yes. I suppose, if I understand correctly, I would hope or imagine that in your counterexample, you still use some sort of non-irrigability.
No, we don't.
No, we don't. Ah,
no,
could
we
you
don't.
please elaborate on that?
Sorry?
Could you please say more on that?
So for this one, it's just like the isoperimetric inequality, and like doing something on larger and larger cubes and closing the singularities, and you don't need any irrigability of the Lebesgue measure. And for this one, we could just invoke this non-irrigability of the Lebesgue measure. But we somehow do it by hand.
Okay, well, I suppose I should read. I'm not sure I understood that.
Yeah. Or maybe, wait a second, I'm confusing. No, the thing is that, yeah, we still use this, for this second family, we still use this Bethuel, like, prove by hand that you have non-irrigability of the Lebesgue measure. What we are able to avoid is the theory of scans by Hard and Riviere. That's what we are able to avoid. So Bethuel uses the theory of scans to estimate the energy of the map that is constructed to prove that there is no weak approximation. We do it by hand. So we avoid the scans, but we still need this thing that if you have a measure that you connect with branched optimal transportation of critical parameter, then the energy blows up to infinity. Sorry. No branched optimal transportation for the first one. No, it's really just like isoperimetric inequality in some sense. I think you could do it with branched optimal transportation, combining this with the computation of the relaxed energy by Giaquinta and Mucci, if I'm not mistaken. But we have another proof which avoids any like heavy machinery and which is just by hand and by the isoperimetric inequality.
Can you comment how is the isoperimetric inequality used in this proof?
Yeah. So as I said, maybe I will try to convince you with one picture. So the core of the construction is to look at a map on a grid like that. So the map is on the cube, on the whole cube, and it goes to the grid. So not the interior, and it's just on each cube you do homogeneous extension. And so you map the cube to the one skeleton. And then you take the grid larger and larger, and then at the end you will take a quotient of this because this is invariant by translation, so you can take a quotient to the torus. But really what's important is to get the estimate when you go to the grid before taking the quotient, and then it's classical things about liftings. And so this means that at each point you have a singularity, which is like this element of the homotopy group of this grid, and you are looking at the minimum energy that you need to get when you want to look at the restriction on a square like that. So it's the minimum energy to realize all these singularities, and it's like it's just the minimal area to enclose all these points. So it's an isoperimetric problem. Like, what's the minimal area to enclose a volume of like a fixed volume? And this is isoperimetric inequality, and it grows. What we really use is that the growth of this energy is dictated by this exponent that comes in the isoperimetric inequality, and which turns out to be also like a critical exponent. So if we would apply this theory of branched optimal transportation, this would exactly be the critical exponent for the branched optimal transportation. And then when you make the computation and you compute the energy to approximate this map, so the energy to enclose those singularities, you get a log, because it's kind of critical. You get a log, an extra log factor, which gives you superlinear growth. Don't think it was very clear, but but yeah, I mean, it's really like what's the minimal area that you need to enclose a fixed volume, and it grows like that, and it's exactly the right exponent that you need to get a superlinear growth of the energy of the approximation with respect to the energy of the map that you are constructing. That's what B.
Have the results concerning this problem of weak approximation for fractional spaces?
I think that so far people have been focusing on W1P, mostly because, I mean, there are technical difficulties, but we believe that once we understand, if we ever understand the problem on W1P completely, it will be just a matter of sweating sufficiently long to get it for WSP. So all the results that I've shown are really W1 something. Here we did the effort of pushing it as far as we could. So actually you can replace 1 by S. So you can do HSP S larger or equal than 1. We are not able to do S less than 1. So we can do this for any high order integer or fractional Sobolev space. And it's really, we are doing nothing. Like, we are taking the case of W1P and just applying in a clever way Gallardo-Nierenberg, and then we get the higher order for free. So it's really like not the difficulty. But we are not able to go below, to go to S less than 1. For instance, here I said that we use Riviere's estimate on the Hopf invariant, and it turns out this is not known for fractional Sobolev spaces. There's a paper by Jean and Armin who are doing it above a certain threshold, but the full range of validity of this Rivière estimate for the Hopf invariant is not known. You cannot let S go down to 0. And I think that if like our proof will adapt to any S such that you have this estimate. So if one day someone comes with Rivier's estimate for the whole range of S between 0 and 1, probably this person can achieve this second result. Yeah, and here there is an issue with the non-linearity of the lifting. You know, at some point we use the fact that when you lift a map, the energy of the lifting is the same as the energy of the map below. I mean, at least they are linearly comparable. And this is not true when S is less than 1. Like lifting has non-linear estimate, and it's very fun because when S is close to 1, this non-linearity is not bothering. Like there are technicalities, but we believe that we can do this. But when S goes below some threshold, then this linearity becomes painful and it doesn't work anymore. And it's the same threshold in both problems, like for completely different reasons. We have two very different things, and there is the same threshold coming out. So I don't know.
Okay, thank you. Thank you so much for your invite and for putting this event all together. Maybe I finally get a chance to explain to my office mates what I did. Okay, so this talk is going to be about 3 papers that I did in my PhD. The last one joined with Guido De Filippis and Alessandro Pigatti. And they're about diffuse decay of excess in codimension 2 for the abelian Higgs model. And for this, I'm going to give you a lot of introduction. In Pisa, probably it's going to be boring for a lot of people, but rather boring than someone gets lost. So hopefully, and feel free to interrupt me at any point if you have any questions. Okay. So in this talk, in the general theme, we're going to talk about models that come from phase transition in physics. And we're going to concentrate on the place where the phase transition happens. Somehow you're mixing water with oil, or you have superconducting and non-superconducting. And these models usually are set up in a way that you are basically extremizing some energy. And this energy somehow forces some type of order in the model that turns out to be geometric and very related to minimal surfaces in many of these things that I'm going to talk to you about. And the model that I'm going to start with of course, is the story of Alencon, which many of you know. But as a brief introduction, so the Alencon model, so think about you have a domain omega, which basically say is a container, and you're trying to mix water and oil inside this container, and you have a parameter u that tells you if you are water or oil. So -1 and +1 for the pure states. And you want to look at the set where this transition happens in between these two materials, and the set u equals 0, or more precisely, you want to talk about, say, the diffuse transition layer is where basically the u is bounded away from the endpoints. Okay, and you set up the energy to be this energy, which of course our favorite ordered, the Dirichlet energy, which actually forces the order in the phase transition, and this one prefers basically your energy to be in pure states, right? So this is a double well potential that is 0 exactly for u equals -1 and +1, right? And then if you look at the stationary points, you immediately see that they satisfy the following semilinear PDE. And you can do a very simple analysis. For example, imagine your domain omega to be almost all of Rn. Imagine it to be very, very large. And in this case, you can get an exponential decay for the energy away from this transition layer. Okay, this is very simple. But this somehow tells you that, okay, the energy is concentrated on a strip of thickness 1 around this transition layer, right? And other places are not as relevant. So you can also, instead of taking the domain to be very large, you can rescale everything down with parameter epsilon and then rescale it properly. And you can say that, okay, if I rescale this picture down, then because of the exponential decay, u is going to converge to ±1 locally in L1 as epsilon goes to 0, and you get the following picture, right? Basically, the transition layer becomes sharper and sharper as you tend epsilon go to 0. And you can do another very simple analysis, very simple computation. You can see you can write the energy, do an AMGM inequality or Young's inequality, and then you can do the famous co-area formula that we all know here. And basically, you see that the energy is lower bounded by a weighted average of the area of the level sets, right? And if you somehow convince yourself that all of the level sets in the transition layer are very close to each other, it's sort of not too bad to think that they are basically approximating the area of one of them, say the 0 set, okay? And the case of equality is basically where equality happens here. So there is a balancing between the Dirichlet energy and the potential. So you get that in basically the normal directions to the surfaces, you solve this following ODE, right? So the model picture that you should think about is basically where you have, say, a surface of u equals 0, and you somehow glued these one-dimensional solutions, which are, I think, arctangent, on this in the normal direction, okay? And rescale down by epsilon. And also another thing you can immediately notice is that, if I minimize this, somehow I should be seeing behaviors of minimizers of this, right? So, which tells you that, this energy should be related to minimal surfaces in a sense. And this has been made rigorous by, of course, Modica and Mortola, where as epsilon goes to 0, these energies gamma converge to the perimeter functional, okay? So the minimizers converge to minimizers. And also, there has been a lot more said about this energy. Basically, you have the conversions of stationary points for the Hutchinson-Tanagawa theory, and the gradient flows also converge to the mean curvature flow. There's also has been a lot of constructions of, say, non-degenerate minimal submanifolds as limits of critical points. And also in the min-max theory, this energy has been very fruitful because of the nice things it satisfies for stable points in low dimensions. Okay, so to here, you somehow are convinced that, okay, this energy is a very good approximation for the area functional, at least in a weak sense. And then you can ask yourself, okay, does this energy inherit any more interesting behavior from the minimal surface regime? And you can ask any kind of behavior, but here we're going to focus on rigidity. And I'm going to state a theorem that you probably don't see it like this, but Allard theorem, you can state it as a rigidity theorem, basically, in the entire case. So if you have a minimal surface, think smooth, whatever. And imagine on larger and larger balls, its mass is very close to the one of the flat plane, then it must be flat. So this is the rigidity theorem of Allard, and you can also, which is the consequence of the epsilon regularity, which is if you have the same bound holding in the ball of radius 1, then in the ball of radius half, you're a C1 alpha perturbation of the flat plane, okay? There's also other types of rigidity theorems for hypersurfaces in the case of codimension 1, which are the Bernstein type theorems, which you have the graphical Bernstein theorem and then the stable Bernstein one, which basically says that in this case, if you, in the case of codimension 1, if dimension is less or equal than 8, and your minimal surface is graphical, then you're of course flat, and then if you're stable and dimension is less or equal than 6, then you're again flat, which this one is sharp, this one, the 7 is still open, so you can try it. So De Giorgi asked the question that, okay, he wanted to see if this is inherited by the level sets of Alencon, right? The graphical Bernstein problem, if it's inherited by entire solutions of the Alencon equation, which is this conjecture. So take an entire critical point of the equation of Alencon with epsilon equal to 1, and imagine it's monotone in one direction. So you are graphical, so all of the level sets are graphical with respect to, say, 1 to n-1 plane. Okay, and then provided that the dimension is less or equal than 8, can you say it's, after some possible rotation, it's just the one-dimensional solution, constant in n-1 directions? And in this form, the conjecture is still open, but with a slight assumption, which, I mean, not so slight, but an assumption of Savin, it can actually be proved. So if you add this assumption, which looks a bit harmless, but somehow gives you minimizing, if you impose that basically, if you go away from this plane, you converge to +1 and -1, not necessarily uniformly. You can show that U is basically one-dimensional. And if I think if it's uniform, it's called Gibbon's conjecture, and it's much easier. And there was a more recent result of this, which implies this, which with more variational techniques of Kelly-Wang, which is the Allard version of this result, basically, which says that if your mass on larger and larger radii is very close to, say, the energy of just the one-dimensional solution, then you must be one-dimensional. This implies the Sobolev conjecture. This is a bit more variational. The proof, which was our starting point for what I'm going to tell you a bit later about codimension 2. But before jumping to that, again, something that probably most of you here know, but the general strategy of these, the proof of these kind of theorems, is basically consists of 2 steps. A first step, very standard, comes for free. You would blow down your entire solutions, and then you use the classification results in the minimal surface regime in the limit to say that, my configuration is looking flatter and flatter on larger scales, right? But then this flatness might rotate. You might not have any control on what this flatness looks like. Then the second step, which is the heart of what you need to do, is basically this improvement of flatness type results, which basically you want to say vaguely, if the configuration is very close to be flat at a fixed scale, then it's much closer to be flat at scale half. And here I'm purposefully being vague with what closeness to being flat means, because it depends on the problem and how you can close your arguments. But you can see that if you are in the entire case, basically you can iterate this and then get the classification. If you're on the local case, you get more A-type estimates, right? So, and the closeness can also be measured in different ways, and it always depends on the linearization of the area functional with the Dirichlet energy, which you know, the harmonic functions are the best functions that we know. So, but actually linearizing this is where the difficulty is. And Sobolen's toolbox, which we looked at first to see, is there any way you can use it? Is the operative word in Sobolen's toolbox is the maximum principle. Always in all of the paper, if he's trying to prove something, it's always maximum principle. And if you go to higher codimension, maximum principle is not so easy to apply. Not impossible, probably, but we weren't able to do anything with maximum principle. Maybe you can. But this means that basically it's very scalar in nature, which why we started from the idea of Kelly-Wang, which is more variational in nature. And here is basically the little history of the codimension 1. I'm going to go to codimension 2. So codimension 2 has a lot of names. It depends to who you want to impress. The abelian Higgs, Yang-Mills-Higgs, Ginsburg-Landau, or U1 Higgs. I don't know the exact differences of them. Just the analyses are hard, which some are different. But I'm going to start with the most general way the energy can look in 3 dimensions. Then I'm going to tell you exactly where we fix and what everything looks like. So you want to make the model codimension 2, right? So you increase the target from R to basically R2. But why R2? Just complex numbers. It's easier. And then you have basically the U parameter again here that takes values in the complex numbers. And then you have this annoying A hanging around, which becomes very useful later, and I will convince you why, hopefully. But there is 3 terms. So there is one term, which is a Dirichlet energy, but it's a bit twisted with basically this vector field, or say the 1 form. There is the potential that we saw, but just with an absolute value. And then there is another term that basically penalizes how A twists itself, right? And in the physics literature I think they say to this parameter the density of Cooper pairs. And it's the closer it is to 1, the more superconducting you are, right? You see basically some topological defects if you look at superconductors under a microscope. And of course, the modulus of U being equal to 1 reflects when you are a pure state and you're completely superconducting. And curl of A is basically the magnetic field, and A is the magnetic potential somehow. Okay. And before describing what this energy is in higher dimensions and everything, the first thing you can notice is that this energy has a huge group of invariants, which is of this form. So if you take U and you twist the phase, and then you twist A accordingly with the differential of this theta, this is for any theta, the energy remains completely unchanged. Okay. So which means that these two pairs are indistinguishable in a variational theory if you're working with the energy. So whenever we want to talk about something, talk about a solution or something, we either I'm going to say up to a change of gauge, or it's implicit that it's with gauge fixing. Okay. But in higher dimensions, you can write it in a more covariant formalism, which I didn't want to write it at the beginning, but it takes the setting is the setting of complex line bundles. And if you don't know what the complex line bundle is, it's just the Cartesian product of complex numbers with a manifold, but a bit twisted, like in the same sense that, say, the Mobius strip is a Cartesian product of R with S1. It's not, but locally it really is. Okay. And basically the function is basically your section now. This is a metric connection, and this is the curvature 2 form of the metric connection. I'm going to trivialize now, which basically means that if you look at one of these local patches and then you write it actually as a Cartesian product, you can write the connection with respect to some reference connection, say just a differential on the manifold minus I some 1 form. And you get the same form back. So it's a twisted Dirichlet energy, a potential, and then there's some magnetic field or the curvature 2 form here, which doesn't really make sense if you say magnetic field in higher dimensions to this. And here the vortex set, which I'm going to call, it takes the transition layer, right? And then it looks basically something like this. Instead of, say, you're concentrating around codimension 1 diffuse sets, it concentrates around codimension 2 diffuse sets. Okay. So, and this kappa is, we're going to fix it to be 1 later, but it's the most general way that this energy can look is basically like this. Okay. But, and the case alpha equals 0, which the 2 last talks were mentioning a lot, the Ginzburg-Landau setting has been studied by, has been attracted a lot of attention. Its analysis is in particular very hard and interesting because of the very slow concentration of the energy. So you don't have it like, say, in the Allen-Kohn setting that the bulk of the energy comes from the jump. Or in this setting that I'm going to tell you, the bulk of the energy actually comes from this concentration set. The bulk of the energy comes from every dyadic annuli outside of this concentration set. So if you have, say, if you're at level epsilon, you get log epsilon of energy. And because of this also, if you have, say, 2 of these vortex lines somehow very close to each other, they see each other and they talk to each other. So which means that in principle, for example, if you expect any minimal surfaces coming out of this, they're not going to be integral, right? And there are examples that you can see that you can get 2.5 as the multiplicity. It's not as nice as the setting of Allen-Kohn. But we're not going to focus here. Actually, we're going to focus with the case that kappa is equal to 1 with magnetic field, which is super nice. Something magical happens that is... so first of all, if you look at the connection, the twisted Dirichlet energy, so the part that gives you trouble in the Ginzburg-Landau energy for this log epsilon is actually the phase, right? But this magnetic field comes and saves the day, right? It aligns itself with the phase, and then it somehow cancels out the energy, and the energy becomes finite. So it's very good in this sense. There's a better thing that happens is this exact equality on R2, which is the base. You want to understand how they look, solutions look in R2 to be able to understand higher dimensions. So with a completion of squares and an integration by parts, assuming sufficient regularity and whatever, you can write this energy as 2 pi, the rotation number of u at infinity in R2, so the degree of u, plus 2 positive terms. Okay, so you immediately, first of all, you immediately get this inequality, and then you want to understand what are the behavior of minimizers, right? So these equations, so if these are 0, these are called the vortex equations or the Bogomolny equations, which pop up a lot in gauge theory. That's as far as I know about Bogomolny equations. But this is the content of the PhD thesis of Clifford Taubes, that he basically worked on these two equations. So you can see this is somehow a twisted conformal condition, and this is just some balancing. But he basically showed that in R2, all stationary points are minimizers. So basically, second order equations reduced to first order equations. It's very reminiscent of Allen-Kahn in R1, in just the real numbers, right? Because if you just put in one dimensions minimizers of the Allen-Kahn energy, you get first order equations, right? So, and also he showed that if you prescribe the 0 set, counting with multiplicity, then the solution is unique. Okay, so it completely characterizes the solutions to this equation in R2, and of course up to a change of gauge. And basically this means that, and noting that all of the energies are basically 2 pi n, it means that it's just a system of non-interacting particles. It's a great model that you want, if you want minimal surfaces in higher dimension, you want the transverse slices to be basically non-interacting points, right? So this is a good candidate. For reasons that it's going to be apparent at the end of the talk, we needed somehow a strengthening of these results to a stability type result. So not just that if it's equal, you are a solution, just that if you are close to, so if this difference is very small, then are you close to a solution? And this was basically the two papers that I was mentioning to you about. And this one is basically an L2 stability result. You can think of it as the quantitative isoperimetric inequality, something like that. So if the discrepancy is small enough, so if you are degree n at infinity and your energy is close enough to 2 pi n, then you're actually close L2 to a solution. I'm not going to talk about these too much here. I'm just going to tell you about the tools. And the main tools here are weighted inequalities. So it turns out that if you write the discrepancy, so if you write the Bogomolny terms and then you write them like R e to the I theta, that you write it this way so that an analyst can understand better what's going on. But you basically get a first term which is weighted around the vortex points, right? They're vanishing like modulus of x to the degree. And the second term. So if this is not here, it's very easy to prove stability. It's just some Hodge decomposition and compactness arguments. And then you pass to the limit. But if this is here, you can't really do much. And for this, the idea is you do a weighted Hodge decomposition. Basically, instead of minimizing the L2 distance to closed forms, you minimize the weighted L2 distance. But for everything, so what is Hodge decomposition? It's basically just elliptic estimates. So you need weighted elliptic estimates. And the weighted elliptic estimates are the contents of this other one, which is a bit, the result is it looks a bit messy, but this is the model case. So basically you can get estimates of this form. This is, if you work in unique continuation, this looks like Carlemon estimates. And actually with Lucas Bolar, we were able to also prove variationally the Carlemon estimates out of the techniques here. But in 2 dimensions, things are slightly better. The only condition you need is basically this, which is very nice for weights that vanish at multiple points. And then some magic integration by parts happens that you get an inequality like this with a constant that doesn't depend on the location of the points. So it's just, and you can see these weights like these are admissible. So why we were able to make the statement a bit prettier instead of just for one vortex. But we're going to use it for just one vortex. So, and then, of course, all of this is assuming the modulus and everything has enough regularity. But then it's a stability result. So you run the gradient flow for a second, like the selection principles in, say, the quantitative isoperimetric inequality. Things get smoothed out a bit, but then you don't go too far from what you were in the beginning. And then you use this result. So it's really in the style of, I think, Cicalese and Leonardi of the quantitative isoperimetric inequality. But anyway, any questions up to now? Okay. So in the sequel, we're going to take kappa just equal to 1. And again, we're going to do the rescaling. And the energy rescales as follows. And then we're going to look in the situation where epsilon vanishes and goes to 0. So because of, in the case that kappa is equal to 1, and this is very brittle, this is, if kappa is not equal to 1, you don't get this. I mean, maybe you get it, but we don't have it yet. You get something like this. So basically the energy decays exponentially away from the transition layer. And you again get this picture with knowing that actually most of the energy is getting concentrated in this tube. And actually the result, which is the work of Pigatti and Stern and Pariser, Pigatti and Stern, which they basically proved in, I think, yeah, right, 2 papers that, or 3 papers, sorry, that the dysfunctional converges in the right sense to the n-2 area functional. So basically you have convergence of stationary points, you have convergence of gradient flows, and you also have gamma convergence. Okay. And if you want to be a bit more precise, you can say that the energy measures, renormalized by this 2 pi, converge as varifolds to a stationary integral varifold in the limit. And you can also say the Jacobians that Antoine was talking about, which is somehow the same, but because there is a modulus, there's a scaling. The Jacobians also converge in duality to a current, with which is supported inside the set of the varifold, right? So somehow this keeps track of the orientation, and this just adds up the orientation, right? In the sense of varifold and in the sense of currents. So having this result in hand, you want to ask that, do you inherit any rigidity in this case? And actually, we asked this problem first in Ginsburg-Landau. In Ginsburg-Landau, it's very difficult, but it turns out this one is more doable. And the answer is actually yes. And you can prove an Allard-type rigidity for this energy. And the Allard-type rigidity up to dimension 4. So again, the one vortex solutions, their energy is 2 pi, right? And basically, if your energy on large balls is very close to 2 pi plus some, is very close to 2 pi, then you're in fact 2-dimensional up to dimensions 4. And then for minimizers, you can get rid of the dimensional restriction. And the way why you can get rid of the dimension restriction is heavily relying on the fact that the stability inequality's power is too sharp. If you get like 2 minus any delta, you get a bit, you get like dimensional restrictions here. And I'm going to say, I'm not going to get so technical here, but I'm going to just give an overview of the ideas and the proofs on what's going on. But before going to say anything about the proofs, I told you improvement of flatness or decay of excess. I need to tell you what is the excess in this setting. So the excess in setting is actually measured in 2 ways. Okay, so the first one is how much energy you have in tangential directions, which you want it to be 0 if the solution is flat. And another one is how much energy, another one is how far you are from solving actually the first order equations on each slice, right? On the slices. Okay. And basically, this full excess, you can write a very simple estimate. So you can write the energy in omega minus the Jacobian, say in E3 to n directions, is actually equal to xs1 plus xs2. So it's also the sum of the two excesses is really the difference of the Jacobian and the energy. Okay, it's just a completion of squares, and it's just an exact identity. And here, this first excess is really in parallel to the excess in the setting of integral varifolds. First, you can notice that it doesn't depend on orientation, right? So you can have, so if you make u to conjugate of u, this doesn't change, right? Or basically, if you change the orientation this way to this way, this one does not change, but this one is actually dependent on the orientation, which it's either a plus here or minus here. Okay, and this one is parallel to the setting in varifolds. This one is parallel to the excess in the setting of integral currents. And again, you can see it also like this, which is the same identity there. So the mass inside, say, the cylinder is the size. So basically, it's the mass of the ball plus the excess plus some very small error, right? And again, we want to show that improvement of flatness with the improvement of these excesses. So the first thing you can show is where you get the classification for stationary points. You can show that if you're close enough and the radius is large enough, then the first unoriented excess decays. Okay. Until you hit this threshold. Okay, so you can immediately see why dimension 4 pops out here. It's just the scaling, it's not anything special, but you can see that if you iterate this estimate from larger and larger balls and stop where this threshold is met and you do it larger and larger, you can get a sequence of radii where, so rk n to the minus 2 limit, let me, rk n to the minus 2, the integrand of, say, xs1 is less or equal than something small o of 1 divided by r2. So if n is less or equal than 4, you get that this full integral is 0. Okay, so you get that you're basically just two-dimensional. And then if you're two-dimensional, you can apply just the result of Taubes to say that you're a solution. Okay, so this is why you get dimension 4. There's a first thing that's very unfortunate here is that on the right-hand side, you have the full excess. On the left-hand side, you have xs1. So this, you can't close the loop, at least in this setting, right? So we don't know what to do here. There's something probably you can do, but it's probably dimension 5 or something. But and for minimizers, you can actually do the full excess because you have an exact identity with the energy and you can construct basically competitors, right? So with this one, we run an alert proof. With this one, we really run the De Giorgi type proof to say that the excess decays. So first, you can show that the full excess decays until you hit this threshold. So basically, you can choose beta, anything you want, and then there exists radii large enough and then threshold small enough such that you decay until you hit this threshold. And here you can just see that you replace this by xs, and then this is replaced by r to the beta. So if beta is bigger than n minus 2, then you're happy. Okay, so you can just take it more than n minus 2. Any questions? Okay. So again, the idea is like before. It's just the black box of the idea that you basically know that the configuration is getting more flat on larger and larger scales, and you want to linearize in the regime where the excess and the epsilon are both vanishing and get some improvement of flatness. And Of course, when you want to linearize in the setting of minimal surfaces, what you start with is you do a Lipschitz approximation of the level set, right? But then here, if we wanted to do what Kelly Wang does, which he basically performs a Lipschitz approximation on individual level sets, and he estimates them all together. Here, level sets are not really accessible because gauge invariance. I mean, the only level sets that means anything is the zero level set, and it's just one, so you can't possibly do anything with it. But you can work with the Jacobian, and you can basically take this Jacobian, which you know that is converging also to the flat-oriented plane, and you can slice this in the 1-2 direction that you have, and then you can just take the body center of this Jacobian, right? And then this turns out to have a very nice estimate. So you get BV estimates just by slicing formulas. And then you can improve it to, with a Lipschitz approximation, you can improve it to a W12 bound on some Lipschitz approximation, okay? And then the next step is basically you want to say that my Lipschitz approximation is actually harmonically approximated. It lives very close, well, small o of xs1 close to a harmonic function. So how do you do this? This is what also abelian Higgs is very useful here, is the fact that in the abelian Higgs, the stress energy tensor is related very closely to basically the Jacobian. And it's because of this vortex equation on slices. And you can basically relate the stress energy tensor to the slices of this Jacobian, and the slices of the Jacobian are the slices of this function, well, in most places. And the stress energy tensor satisfies a nice equation, it's divergence free. So basically, you can see that in some off-diagonal elements, they are very related to each other, and actually you can get an equation like this, which is exactly what Allard gets in his paper when he wants to do the harmonic approximation, right? And then what you do, which is somehow at the heart of Allard and also our proof, is basically you have a sequence of approximations like this, and they also solve a very weak elliptic equation, right? So if you renormalize this by square root of xs1, you immediately get that you can extract convergent subsequences strongly in L2, and that limit is going to be harmonic because this xs is vanishing still, right? So with this, you can immediately say that, okay, my function lives very close to a harmonic function. And at that point, you can just do a Cacciopoli or a height xs, which you know from elliptic regularity. And with a Cacciopoli type inequality, you can get an xs height bound, and you can conclude. But this is also where the threshold comes from. Basically, where when you do xs height bound, you're not really doing an xs height bound. The height is a bit diffuse. That's the problem with all of these diffuse models. But then how much is it diffuse? The diffuse is exactly epsilon squared. So you get errors of order epsilon squared or 1 over r squared. Okay, and and you can improve it a little bit from dimension 3 to dimension 4. It's just technical things. And this is how you can exactly do it in the case of stationary points. And you can also use this. So we were trying to see if you can do anything in higher dimensions and for minimizers, and we were somehow stuck. But you can notice that also with this theorem 3, which is somehow, you can get a diffuse regularity. You can somehow, you can't say too much about the zero set exactly, but you can iterate and stop at scales epsilon, and then say that, my zero level set, I don't know if it's exactly regular enough or if it's flat, but I know it actually lives in epsilon close to a harmonic function or something very nice with uniform estimates. So basically, if you can iterate this, the full case is just open for Gibbon's conjecture. So you can, if you want to for example, if you want to start thinking about this problem in the stationary cases and higher dimensions, you can assume that globally your zero set is contained in a size 1 tube. So this actually gives you that. And we can use this in the case of minimizers to build competitors. And this is going to be the, which I have 10 minutes, this good. This is going to be the last part. I'm going to just show you with a bunch of pictures. Hopefully everyone's tired from all of the talks today. So I was not keeping any equations for the last slides. So I'm just going to show you with illustrations what's going on and what's happening. So basically for the decay of full excess for local minimizers, you can, so imagine you're in 3D. And I just want to show you what happens in 3D. So imagine your zero set a priori looks like this. It's not flat, it's pretty bad. And if you were just arguing for, say, currents or for just curves, and you know that this was minimizing, you would like to cut and replace it with something with less length, and then get a contradiction. But here you can't immediately do that. But you know that it lives epsilon close to a line, in 3D at least. You can take 2 slices, and then you can replace it with a line, and then you can take a one vortex solution and then put it on this line, and then pull it back all over this line to mimic it in an energy level, right? And then you want to basically say that the energy of this is less than what I started with, so I need to have some improvement of flatness. But this is not yet a true competitor yet. So what you need to do is you need to attach basically to the boundary, right? And this was the part that we were stuck for a long time. And what you do is that, first of all, the slice that you choose is up to you. So you can choose a slice that the excess 2 is very small, right? And excess 2, based on the stability things that we saw before, basically shows, quantifies how close you are to a solution that you put here, okay? So then you can just interpolate in between these two and be done, but there is a gauge invariance. Interpolate in what gauge, who knows? And then in this picture, it's pretty easy because it's just 2 slices, right? You can just gauge fix this slice and gauge fix the other slice and then attach. But in higher dimensions, what can you do? It becomes very complicated, and with a lot of sweating, you can, so if you zoom in this region, in the interpolation region, and then you start covering your set with very small cylinders, like very thin aspect ratio cylinders. So epsilon and beta, epsilon and ln epsilon. And then you gauge fix inside each one of them very carefully, and then you attach them with a partition of unity. And then pray that everything just works out at the end. And somehow everything works out. And the reason is that if you choose these well enough, such that in the overlap regions, you have higher order estimates, when you attach them with a partition of unity, you don't pay too much. At least you pay something that you can control. And why do we choose this height to be epsilon ln epsilon, which is basically because of this fact. Because if you just ignore everything away from the vortex set, this exponential decay comes and gives you this 1 over r to the beta. And then while you're attaching things, you pay factors of log epsilon, which doesn't matter too much. And then when you gauge fix, you can attach, and then you can just compare. And then when you compare, you get to a contradiction, and you can conclude. So in short, you can actually get the decay of excess, the decay of the full excess for minimizers. But however, I'm going to say just what I think it might be helpful for higher dimensions, but I'm not too sure, is that for dimensions bigger than 4, there is this term that you also see in Allen-Kahn, which is called the discrepancy. It's somehow how much your equation is solved at each point, the balance. So in the Allen-Kahn setting, you see the potential minus the absolute value of the gradient. But here you see, you should replace it with the potential minus the curvature. And this equation solves an equation that has both xs1 and xs2 in it. So you might think that maybe if I can close the loop in theorem 3, somehow you get, maybe if you can close the loop and bound this above by xs1 again, maybe there is some hope. But even if you do that, you might get to dimension 5, maximum 6. Maybe at this point you have to just do something else. For example, it would be very interesting to see if there is anything you can mimic out of Solvin's toolbox. So if you can find some distance function that is subharmonic in directions other than just one direction, or something like that, but we don't really know. And it's also, this is a method that it's not too far. It's well known. It's just the implementing it is very hard. And the thing is that you possibly can do this in other approximations, in other diffuse approximations of minimal surfaces, say in other codimensions that have, say, some type of Bogomolny equation. For example, if you, for the Yang-Mills, for the Yang-Mills-Higgs, for the SU2 Yang-Mills-Higgs setting, there's also Bogomolny equation, but the theory in just the stationary points and the gamma convergence and all of that is still not done yet. So, and also it's very interesting to see if the Ginzburg-Landau energy, you can get anything from the Ginzburg-Landau energy with this pipeline. For a while, I think you can get the excess to be of order 1. I don't know if you can get it more than that, but you can get that for free with Neighbor-Valtorta type techniques. You don't need to do anything too much. And also there's, if stability gives you anything in the abelian Higgs model, which I don't know exactly. The only result I know out of stability is just that you can have classification of stable points. You can also reduce the second order equation to the first order equation on some special, say on T2 or S2. Other than that, I haven't seen any work done on stability. I don't know if it's hard or if no one studied it, but the operators look very ugly. It's just what I saw. And also, there's always hope that minimal submanifolds from these diffuse models can be a bit better than what you get just with varifolds. But, and in the case of Alencon, in some cases, there's slightly, in very technical cases, they're slightly sometimes better, but here it might be that just doing more things with the abelian Higgs model would just get to a dead end. It might be that they're just not better than any, they're not any better than just the things you can get in varifolds. Yeah. And I guess I stopped a bit sooner than here, but that's it. Thank you.
So can you explain? So you said something at the end, you can sort of get, for the classical Ginzburg-Landau, you can get the excess to order 1 by Neighbor-Valtorta. So what exactly would you get?
You can get it at, say, scales of epsilon to some alpha, but then actually trying to patch them together, you might need to do some harmonic approximation or some things like this. But I don't know if it would be useful in any sense. For example, it wouldn't even give you uniqueness of blowdowns, for example, if you get something like that. So it seems just genuinely just difficult. There are some things you can probably do in dimension 3, because in dimension 3 it's just like geodesics. It's just, yeah, and you get some really nice equalities instead of inequalities. So for example, in this case, one of the things that really saves you is that the Jacobian and the energy are very closely related. But in the Ginzburg-Landau setting, the Jacobian is just like, something else from the energy. The energy is like a log epsilon order bigger than the Jacobian. So you might want to just, see if you slice the energy, what happens, but then you're slicing, you're like slicing variables. Doesn't make any sense. But in 3 dimensions, you sort of can. There's some things that you can do, but I don't know if you can do anything more than that.
Yeah, so in this case, basically, you have that for any minimizer. Any minimizer is 2-dimensional in any dimension.
In any dimension.
So it's not like for the the scalar case, the Giorgi conjecture where you have a counterexample in higher dimension.
Note,
So
note for this you have the bound. You should have the bound. If you don't have the bound,
for the energy bound.
Yeah,
The bound dimension is hidden in the energy bound.
yeah, exactly.
Okay,
Yeah.
okay.
I mean, if you can get, if you can get any classification in codimension 2, let's say you have to be the flat one with one multiplicity, you can just apply this. But
Yeah.
I don't know if you have anything like that in codimension 2, or it's very difficult at least.